Hello, my name is John Rivette. I'm the Associate Professor of Painting and Drawing at West Texas A&M University, and I want to talk about these two murals that we put in the Natural Science Building this fall, 2021. All right, here are two stills of the murals, and here are some facts. The murals are about 9 by 24 feet. They were painted over the fall semester by the WT Mural Squad, which is composed of WT art students, and I am eternally grateful to my wonderful students who did this because without them, none of this would be possible. Also, you might notice that the murals are entitled the Crossman-Flynn mural and the McGovern-Craig mural, and this is because we like to make our murals site-specific, meaning that they relate in some way to the space where they are painted. And the way that these murals relate to the space is that all of these scientists actually gave us data that we used and made into visualizations to help inform us in the color choices and the composition of the murals. To further illustrate the idea of site specificity, here we see another mural entitled Who We Are in the Panhandle Plains Historical Museum. This mural is site specific in two ways, through the pattern that we use to compose the mural and the colors. The pattern is an interlocking circle pattern to represent a lot of the circles we saw throughout the entire museum, including in the room where the murals are placed, which is the derrick room. And if you look at the derrick, you will see giant wooden circles of the gears and the motors that move the well. The other way is the color or the palette of the mural, and that comes from somewhere else in the museum. The colors for the Who We Are mural come from this painting entitled Early Washburn by Ignaz Ahula Dick. Apart from being one of my favorite paintings in the entire collection of the museum, we chose this because we love the colors of dawn that are in this picture, and it represents a new day, which was sort of the spirit that we wanted to capture for the mural. So the first step in planning of the science murals was to find a pattern that related in some way to science. What you see here on the left is a hexagonal tile. My work generally deals with tessellations or repeating forms, and I develop these by sitting down the old-fashioned way with a ruler and a compass and draw them out. I really liked this tile that I had drawn due to the other at thing on this page, which is a QR code. If you put your cell phone camera on this, it'll take you to a YouTube page with a video entitled Hexagons are the Bestagons, where it explains how hexagons are reoccurring in nature. And I thought this is a very appropriate shape to use in a mural that would go in a natural science building. The next step in planning of the mural is to find the color palette. And as if you notice from the Who We Are mural, I like to often start with the idea of art from art, where I find a work of art to inspire me. What you see here are science murals done by Raymond Johnson and the science building on the campus of University of New Mexico that we visited with students this summer. The Raymond Johnson murals became the starting point. So what I did was abstract them into these broad color fields, then applied them to the tile that I had developed. What you see here is an animation based on those ideas where I run the pattern at different scales and directions to determine what I like and what I don't like. I look at these animations like visual experiments, and much like what happens in science sometimes, you don't get the results you want. While I did find some of the images interesting enough to turn into prints that I showed at an art show I did in Amarillo this fall, none of them really had the visual effect I was hoping for the science murals. One of the ideas I thought of when I was first approached about this project was the idea of data visualization. And for some reason that made a lot of sense to me because scientists make data, and if I can make pictures of data, then maybe that's a unique thing to do with this mural project. So to get some data visualizations, I had to go to a very unique source. And this is my son, Isaac Rivette, live from New York City. Isaac, you want to tell the people out there what you do?
Yeah. Currently, I spend most of my days working at Twitter as a research specialist, working on different projects focused around like advertising and marketing research, working closely with companies in the tech and telco sector. Basically, they advertise on Twitter, and then I do research to discover, is that driving any kind of increased revenue for them, and then, doing analyses around just, all of our research in general. So, developing new kinds of research that they do. Using Twitter data. That's what I do. There's a lot to it.
Yeah. So simply put, you're a data analyst. You lived with me for a while last year, and I remember one of your friends pulling up some screens, and I looked at the screens and go, "Hey, those are pretty cool pictures." And so you and I had a conversation about how we could use data to create gradients that I could start using in my art. And so when the science mural came forward, I said, hey, this is a really great idea. And then I went and asked for science data. And then when we got some, you took that data and what did you do with it?
Well, put simply, I ran it through some different kinds of code, simple code. There's like some Python, and then output different kinds of visualizations that looked, honestly, at this point, they just looked visually stimulating. This was more of an experiment, but yeah, that's the simple.
Yeah, and we didn't really, the goal of this is maybe to explore data and visualization, but really we did want to kind of to make it look good, which was the first rule. So it's definitely more of an abstract approach. So why don't we go ahead and pull up the slideshow? All right, first off, we have Dr. Eric Crossman. He's the assistant professor of environmental science. He provided data from a study about the intense heat in Palo Duro Canyon. The data temperatures are from May 16th to June 24th. What did you do with that data?
Basically, it came in different kinds of data, came in different kinds of formats. And so I had to, first thing was just clean and get it ready, make sure it's in the format we need, which is, simple rows and columns, as long as possible, as much data as possible, as wide and long as the data set can be, is basically what I tried to make it. That's what they call it.
So what kind of visualizations are these?
This one here, both of these, the one on the right is pretty simply just a heat map that doesn't have a lot of data in it. And then the one on the left is what they call a distribution plot. Basically, these are made with some Python code. I use a service called Seaborn, is a popular one. And basically you input data and it visualizes it for you. And in this case, on the left is, like I said, a distribution plot, which basically focuses on measuring through colors, like the distribution of different data points. So you can see as we go along, you can see on the left side of that screen, the y-axis has numbers going from 1 to 30,000. And as you move along that, another value, that's the color value, changes as you go along that. So, as you go from 1 to 30,000, you get different secondary values, which in this case, lighter green is, closer to 20, darker green is closer to 40. What those numbers mean at this point is from that data set. For this experiment in general, I think we were focusing mostly on just, seeing what looks interesting when you visualize graphs. And like, as we move forward, what kind of data sets would we want in order to use these types of visualizations? I personally went through a lot of different visualizations for these projects, 16, 20 different types, and finding a distribution plots and then heat maps, which is the one on the right. And if I move over one more slide, you can see this is the other version of the heat map. So this one looks more exciting. It kind of looks like an asteroid or something, like shooting into the sky or into the ground.
Yeah.
And basically this is just a heat plot. So like the other one, the color represents a certain value, but then it also allows you to use an X and a Y axis as well. So we're talking 3 different values. We have the value at the bottom, which is labeled 1, the value on the left side, the y-axis, which is labeled 2, and then the color going from dark red to dark green is a third Z value. And that's what this one is plotted. Looks pretty interesting.
Yeah, those were pretty interesting. I actually tried to use those at first. I just didn't seem to work for our project. I think if we had more of a full rec square, it would work a little better. But I think the next slide is the actual image I ended up using for Dr. Crossman's data, which, it's relatively simple. And this one is the correlation plot. Is that correct, Isaac?
No, this one's still a distribution plot.
Oh,
it's the same one as that green one. It's pretty much using different values and different colors as well.
This is Dr. David Craig, Associate Professor of Physics, and provided data from the Alpha Galaxy Survey. He teaches our astronomy classes, which I always try to get my students in, but they always fill up. The data is based on the total power from the signal from the neutral hydrogen, as well as the galaxy positions as seen from the North Celestial Pole. And I think you just did kind of the same data plots for them, but we can kind of look at what they look like.
Yeah, they look really different in this case. So if you remember those like meteorites, like these ones that we're looking at, we have these. And so they look drastically different. They don't, because of the data set, just the different kinds of data sets you get, the same plot looks, completely different. While the colors are the same, physically it looks very different.
Yeah.
Virtually, I guess.
So yeah, but I really like these two. I tried to use them as much because they were filling the space a little bit more. I do find them interesting.
But then with this one, I think we got some pretty awesome distribution plots.
Yeah, very pretty. And actually later in the slide talk, I'll talk about where these kind of reminded me of. There's some artists that really do make work that look like this. But then again, I use this kind of simpler one at the end because I think again, we started developing a color scheme. And as you can see, the two predominant colors. I think the next doctor is Dr. Nick Flynn. He is the associate professor of biochemistry, and he gave us data from the study of amino acid content of bone broth, including beef and chicken.
Yeah, these are distribution plots. What's interesting is if you look at these plots, this repeating pattern is actually not necessarily in the data set. The reason why the pattern looks like it does is because this data was given in different data sets. So there was bone broth for like different kinds of meat. And so basically, in order to make it like a large enough data set to use to make this image, I had to combine them all. So really you're seeing like each stripe from where it goes from dark green, for example, to bright yellow, and it kind of repeats. Each like group of patterning or whatever is a separate, piece of meat. Now this is, I think, an interesting comparison looking at how a heat map, like different kinds of data sets look in a heat map. This one's, a heat map. And so it kind of looks like a correlation matrix because it's so blocky. I mean, sort of, but the reason it's like much blockier and more pixelated, almost like it's like an 8-bit image or like a 2-bit image or something versus, if we like looking back at the other same heat maps that were much less block, they're like pixels are smaller and finer and looked more like really like an 8-bit piece of fire. And this is just looks like some squares. The reason for that is like the amount of data points. So the density of data makes the density of these graphs better. And so this was not as dense of a piece of data. We're talking, maybe like 120 data points in length from top to bottom. And so, you get definitely smaller heat maps. And this is just more of them.
More of them. We did a lot. And this is the one I ran with at the end. Again, I really like the striations. So as you said, it changes between the broth, which I found very interesting. Yeah. And actually what I did in the murals is I turned these on their side. And then last but not least, we have Dr. Gregory P. McGovern. He is the instructor of chemistry. And he provided data from their nuclear magnetic resonance spectrometer, which allows the molecular structure of a material to be analyzed by observing and measuring the interaction of nuclear spins when placed into a powerful magnetic field. I had to look that up. I had no idea what a nuclear magnetic resonance spectrometer was. And I don't think he actually told me what they were analyzing. But again, it did provide the most simple data, I think, which actually I kind of enjoyed.
Yeah, it just depends because it's not like this. It's very, very clean, very minimal. There really is a lot of data points here, but I think because when you're looking, I don't know anything about the data behind nuclear resonance, but it seems like from this visualization that like the data is not, the variance in it's not very high except for like little bits, jumping out like that. So it's a pretty consistent data set, even if there were a lot of values in it.
Yeah, definitely. And again, we got
here as well.
Much with the distribution plots, yeah.
Like if you look closely, it looks very continuous, almost no change with little blips, like yellow line in it. In the red would be the same thing as this. It's like flat, and then jumps up, spikes up, and then comes down. So it's basically this consistent line with random variances, and this is that same look, just in a different format where it's red, yellow, and then like little bits like that.
That's interesting. I like these, but I think the one I ran with was even though it's not perfectly smooth, I like this one because it looked very smooth. And that sort of was the odd man out pattern that I used in the murals and sort of counteracted to the different linear ones that I chose to use for the mural. But that's kind of all of the data we used. And so I think Isaac and I really enjoyed working on this. We definitely want to talk about doing more things like this in the future. So Isaac, in the future, if we were going to continue to work with scientists, what would make these plots and charts and graphs look a little bit more interesting, or what help us get a little bit more of a dynamic aesthetic?
Honestly, I think ideally you would want to actually work with a scientist. It's like in this case, it was more of a request for data that you put out, and then that's what we got back. And then I just like went through the data, but not knowing much behind it. But I think what would be more interesting is generally when you're working with like scientists and researchers, all this data visualization that I'm talking about, I do research just in a different field, not academics. And like, they know these same skills I have. They know how to make visualizations and generally know how to make these same images the whole point is to effectively tell a story about the data you're observing in a simple snapshot. You don't have to read 100 thousand, lines to know what's there. You just look at an image and the color tells you. Um, I think that's what's really interesting with visualization. So it would be fantastic to work with a scientist who's working on an issue. They know that data in and out, and then work with them. What do you think would be a visualization that most effectively shows what you're trying to get across? Um, for example, if they're trying to get across, if it's you work with a scientist who's trying to predict like precipitation in an area and they want to tell a story about reduced precipitation because of climate change, you work with them. What's a visualization? Some kind of heat map, or is it not a heat map? Is it a bar graph? And then what is it? And we want it to be exciting, but I think also part of the challenge turning into a mural might be looking at a visualization that isn't actually so exciting. How do you turn that into a mural? But
that would be my
said,
job.
Yeah, exactly.
That would be my job. Well, you could figure out my patterns could be like graphs. We could figure out new ways to plot it. So it'd be more back and forth. But I think the goal for me with this project was just to show the potential of what we could do with this. And then maybe if we had people who are very interested in making it happen, more data visualization that could be readable so you could actually look at the mural and understand it. This would at least start that conversation, which was the goal of this project.
Yeah, I agree.
Yep. So Isaac, thank you for doing this. I really appreciate taking time out of your busy New York City Twitter lifestyle. And we will hopefully work on these projects in the future.
Definitely. Thank you.
Yep. Thank you. So after all of the multiple data studies, these are the 4 data sources that I chose to use as inspiration for the murals. The reason I chose these is because of the art of Bridget Riley. Here are 2 pictures I've taken of her paintings. And while she has a variety of different styles in what we had known as the op art movement, I really enjoy her striation paintings, which represent a different amalgamation of colors and arrangements to optically affect the viewer. The next step is to make digital sketches for the murals. So I took this data, and the yellow is Crossman and the blue is Flynn. And what I did with the Flynn is turn on the side, and both I turned into more abstracted gradations or striations based on a limited color palette. And here's the McGovern-Craig. Craig again is the blue, and McGovern is the yellow. The Craig I also striated it in the abstract fashion using the limited palette. But what I did for the McGovern aspect was take that smooth gradient and make it into several steps, which is a trick I've done in former paintings. After the digital sketches are there and the limited palettes have been developed, then I make these insane hand-drawn graphs to kind of determine where they will go in the colored fields. And this actually helps the students paint the murals because essentially I create a paint by number or paint by letter system to where they know where to put the colors on the murals. To get to the final design takes a lot of effort and study. So we see first me using some animations with the heat map data. Then I moved to the more mature ones. I made about 45 versions of this, which you see here. So on top of all of Isaac's data studies, this process takes a really long time to get a final result. After that, we get to work. We strap a giant piece of canvas to the wall in the painting room, then we project onto it and we trace out the image in charcoal. Then what you see here are students going over those charcoal lines with gold paint. We also use blue paint on the other one, but this process did not take very long, maybe 5 hours for each mural. After drawing comes painting, the fun part. What you see here is my advanced painting class working on the mural. When they finished, I had the beginning painting class work on the second mural. They took a little bit longer, so luckily I have a loyal group of student workers and graduate assistants to help. Each mural took about 2 weeks, and one of the things I really like to do is to give all of my students professional experience so they can take some of these skills out into the real world and make some money. What I do here is break the colors down into set color schemes. And so what you see the students doing is applying 14 steps of blue and 8 steps of gold. And this paint by number method really works because it allows people of all levels of painting to execute the mural. The nice part about working on that giant piece of canvas was portability. What you see here is us building the stretcher bars. So when we took it off of the wall, we towed it over to the Natural Science Building, built these stretcher bars, and then stretched the canvas and put them on the wall. We had to get them about 20 feet off of the ground. And this is a little nerve wracking when you think about it from a safety aspect. So we had to bring in the professionals. We had SSE, the school maintenance crew, come over and help us. They brought about 4 guys, mounted a French cleat, and hung these up using these lifts. This portion of the project took a full day, and it was fascinating to watch. The entire project, from the moment I was approached till we got them up, took over 6 months. Once they were finally there, the feeling of elation and relief was unmatchable, and they really look wonderful in the space. I'm very happy with the results. And that concludes the making of the NSB murals. I really would like to thank Dr. Rebecca Bachman, the Dean of the Paul Engler College of Agricultural and Natural Sciences, for bringing this project to me. I would like to thank Dr. Crossman, Dr. Flynn, Dr. Craig, and Dr. McGovern for giving me their data. I would like to thank my son, Isaac Rivette, for spending his precious New York City time on making the data visualizations. I would also like to thank SSC and those awesome guys who put that mural up on the wall. And most importantly, I really would like to thank my students who made this project possible. Again, my name is John Rivette, Assistant Professor of Painting and Drawing and Art Program Director at West Texas A&M University. And I want to thank everybody for spending their time to watch this video on how we made these natural science murals. Thanks.